Okay, that first video was getting a little too long, so sorry for the abrupt ending to that. But let's continue with part 2 of aldehydes and ketones. We're in the middle of synthesizing ketones. And the best way was covered at the very end of the part 1 video, where we're looking at pyridinane, or one of the strong oxidizers, to take a secondary alcohol and make it into a ketone. Hey, here's a new way of doing it. It's the use of a Gilman reagent with an acid chloride. So let's review Gilman reagents real quick here. So that's a series of reactions we saw last semester. They're also called the Corey-House reactions or reagents. And what you do is you start with a primary, secondary, tertiary alkyl halide. You can also use vinyl halides. So remember what vinyl halide is? That's where you just have an alkene, and to that alkene carbon, you attach a halide. There we go. You can also use aryl halides. So the start of the Gilman reaction is very versatile. Lots of different compounds can work. You can use chlorine, bromine, or iodide as your halide, but not fluorine. There we go. And what you do is take one of those. Here, why don't we just take, I don't know. Let's take 1-chloropropane. Okay, and we have 3 steps, 3 reactions in the Gilman reaction. First, we add lithium metal, and the lithium exchanges with the chlorine to form, oh, this is N-propyl lithium, I think is the common name for it, or 1-lithiopropane. You don't have to name it. And then you add copper iodide, copper 1 iodide, and then this is where you make the Gilman reagent. So lithium is replaced by a copper, and copper adds 2 alkyl groups. Turns out the copper now has a net negative charge, so you need a lithium counterion there. This is actually the Gilman reagent. And sometimes, you know, we take a shortcut when we draw this. Instead of drawing the same propyl group or whatever group we started with, instead of drawing it twice, you know what? Why don't we just draw it one time? And we'll put that group in parentheses and put a little 2. Now you can put the lithium on the outside next to the copper, and then CuLi. I had some students call that the Cooley reagent. So it kind of looks like if you're going to pronounce that. And that is the Gilman reagent. Okay, and then last semester, to end the Gilman reaction, Corey-House reaction, you then must add a methyl or primary halide. Secondary and tertiary halides, aryl halides, no. Vinyl halides, no. You have to do something that is not very crowded. So I don't know, how about, yeah, you could use methyl chloride, which is what I was going to draw, but you know what? Why don't we use ethyl chloride? And then what happens is the point of attachment where the halide is on this primary or methyl halide, that's where this carbon of your Gilman reagent adds. So we have 3 carbons coming to meet these 2 carbons for a total of 5. So right here, these 2 carbons are there. Kind of identify which carbon had the chlorine. And then we're going to flip this around and upside down, right? So these 3 carbons are here, and you link them end to end, and you got 2 carbons plus 3 gives 5. You make pentane. Kind of boring. Kind of, you know, pentane is pretty cheap. It's the expensive way of doing it. You can also make ketones. All you have to do is, instead of a methyl or a primary halide, you add an acid halide or an acid chloride, turns out. So take the same compound here, but now add a double bond O on a carbon that's also attached to chlorine. And that's your acid chloride. also called an acyl chloride. And same exact reaction. We got 2 carbons, but this time the 2 carbons have a double bond O, and then you add your 3 carbons on the other side, link them together, and now you have a ketone. Really nice. Yeah. And so sometimes on exams, we might reverse this. What am I talking about? I'm not doing synthesis. I guess you could do synthesis, but we have, there's another way to write this exact same reaction, right? In this example on the screen right now, we have the acid chloride over the arrow. And we have the Gilman reagent on the left-hand side. Both of those compounds contain carbon, so the organic chemist can choose either one to put over the arrow or off to the left side. So you can write the same exact reaction this way. Put the acid chloride on the left, and over the arrow, put the Cooley reagent. And it's going to make the same product because it's the same reaction. Okay, and now the focus is on, hey, take this carbonyl group and make it longer and turn it into a ketone. There you go. There's a second way of making ketones. And I think we're done with synthesizing aldehydes and ketones. Let's move on to reactions. Okay, first thing we need to know is that, remember when we said that when we're naming aldehydes and ketones and both functional groups are in the same molecule, there was a tiebreaker, right? The aldehyde group just squeaks by the ketone group in terms of rank. Aldehydes are more higher priority when you're naming by the IUPAC rules than ketones. And perhaps the reason for that is, in nature, aldehydes are more reactive than ketones. Aldehydes are more reactive than ketones. So you can actually exploit that characteristic. We know that sodium borohydride, for example, NaBH4, reacts with both aldehydes and ketones. If you have a molecule that has both an aldehyde and a ketone, you can just treat the molecule with one equivalent of sodium borohydride, and it will first attack the aldehyde, and then when all the sodium borohydride is used up, then the reaction's over. The aldehydes, all the aldehydes in the molecules will react first before the ketones. You have to do a little bit of math here, right? You don't use 1 mole of NaBH4 and 1 mole of this compound. No, because there's 4 hydride ions, right? So really, you're going to use 1/4 of a mole of NaBH4. So that after you do the stoichiometry, you'll have 1 mole, 1. You'll have 1 mole of hydride ions. In this molecule, you have 1 mole. If you like the math, there it is. The shortcut is, instead of using moles, use the word equivalent. And that's going to take care of it for you. It's understood that, oh yeah, if you only have 1 equivalent, we're just asking this molecule to react 1 time. And it'll happen at the aldehyde. Sweet. Sodium borohydride is not the only reagent. Other reagents also react first with aldehydes. Aldehydes are just more reactive. Cool. Okay, and as a case in point, aldehydes are easily oxidized because they're more reactive, and ketones are not. Well, there's an exception to that, but we're not covering that in this level of organic chemistry. So let's just take an aldehyde. I don't know. Here's an aldehyde. And then we can oxidize it to a carboxylic acid with the use of several oxidizing agents. So maybe we'll pick KMNO4. You know what? It's not too surprising, I hope, that this is what's happening. KMNO4, chromic acid here. No, is that chromium trioxide, sodium dichromate, potassium dichromate. Those are the strong oxidizers. Oh, I don't have to write it. It's right here in our key concepts. We were introduced to those when we were oxidizing alcohols. And we said in the mechanism, we didn't say the mechanism, kind of a pseudo mechanism. We said what happens during the course of the reaction is that the strong oxidizers first oxidize primary alcohols to aldehydes. But then the strong oxidizers attack again. And they take these aldehydes and make them carboxylic acids. And if you remember that, then this totally makes sense, I hope. Right? If you just start with the aldehyde and add the strong oxidizer, you get the carboxylic acid directly. There we go. Cool. No mechanism on the exam. And then here's a little thing. If we ever get back into the lab, please replace the caps on bottles of aldehydes, because oxygen gas is an oxidizing agent. Makes life possible, helps us metabolize food in our body, glucose, get energy, and it reacts slowly with aldehydes just on standing. Even without a catalyst, just some air. You don't need a tornado, but that was kind of a neat little graphic. If you have an aldehyde and you leave the bottle open, you'll start to slowly react the aldehyde with oxygen from the air, and you'll start to make carboxylic acids. In fact, it's very common to have a bottle, that's not a bottle, it's a round bottle flask, whatever, of benzaldehyde. And that's a liquid at room temperature. And then if you let it sit out in air, it turns into benzoic acid, which is a solid. So it's a nice indicator, if you will, of how old the bottle is. So we used to, I remember seeing old bottles of benzaldehyde in our stock room, and you have your bottle here, what a ugly bottle, and it has a liquid in there, and there's a big clump of solid sitting at the bottom because it's slowly being oxidized, and the benzoic acid is precipitating out. Okay, so in case you use aldehydes in the lab, keep them closed as often as you can to prevent the slow air oxidation of those aldehydes. I think we're done with oxidation reactions. Let's double check. What else we got up here? Yeah, we are. Okay, we're actually going to begin, just kind of preview in a sense, the last key concept for Unit 2. Technically, it's Unit 2, Part 3. And there's some verbiage here. You can read this paragraph on your own. I'm going to just hit the highlights here. Before we dive into the final set of reactions for aldehydes and ketones, I just thought it'd be useful to kind of talk about the difference between aldehydes and ketones that have the carbonyl group, the C-double bond O group, and something called carboxylic acid derivatives, which also possess a C-double bond O group, right? Turns out they are very different sets of carbonyls, C-double bond O. And I want you to just get a feel for that. More importantly, I just want to impress upon you that when you're studying organic chemistry, you got to put the aldehydes and ketones in one box and all the other C-double bond O functional groups in the other box, and keep them separate. Occasionally they look like they react the same, but most time they're going to produce different products even with the same reactants. So I'm going to show you an example of that today. Let's highlight a few of these differences. First of all, what are the so-called carboxylic acid derivatives? If you take some calculus, right, you know what a derivative is. If you have this function and you take the derivative, you make a new function out of the original. You take the derivative and bring down the 2 and subtract 1. And if you remember calculus, you make a new function out of the original. And so that's what we're doing here. We're borrowing the term from math and saying, hey, let's start with a carboxylic acid and make a derivative. Let's change this functional group into something else. So let's replace the OH with a chlorine, and now you have an acid chloride. If you replace it with another carboxylic acid with the hydrogen removed, that makes an acid anhydride, or simply an anhydride group. We're not going to cover the thioesters, but they exist. Replace the OH group with an S and some carbons, sulfur and some carbons, you have thioester. An oxygen with some carbons will become an ester, and then nitrogen in here with hydrogens or with carbons on that nitrogen, that forms an amide. And so here are the 5 most common carboxylic acid derivatives. Every one of these has a carbonyl group. Okay, and what you need to know is that aldehydes and ketones react extremely differently than acid chlorides and hydrides, thiol esters, esters, and amides. Some of you are like, okay, great, I got the information, I'm going. Cool, see you in a minute. You can fast forward to the next set of reactions. Others like more reasons. It helps you to remember. I'm not of that persuasion myself. So why? That helps me remember. Okay, here's one explanation. Up here it talks about stability. Lone pair stabilizes the carbonyl. What are we talking about? So what you can do is draw a resonance structure. It's not a very stable one, but what you can do is say, hey, hey, pi bond, why don't you move up to oxygen, become a third lone pair? And that'll give oxygen a formal negative charge and the carbon a formal positive charge. I know it's a carbocation, that's not stable. But if you draw this resonance structure, the aldehydes and ketones, they're like, we're really unhappy with this. Why are you doing this to us? Yeah, don't do that. Go back to the original form. The carboxylic acid derivatives, however, are kind of like, oh, this ain't too bad. So move the pi bond on the oxygen, create the carbocation, but every one of these carboxylic acid derivatives has an atom next door with a lone pair. Everybody has one. And they can use that lone pair to create another pi bond and a third resonance structure. And so now what we have are more resonance structures, so the intermediate is more stable, and we don't have a carbocation anymore. So hey, this is one explanation as to why aldehydes and ketones extremely reactive, maybe because sometimes they feel this carbocation and boom, they need to get rid of it by reacting. Or you can think about the carboxylic acid derivatives. If they try and create that carbocation in the resonance structure, the lone pair on the neighboring atom quenches it. Said, no, 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 let's give you back your pi bond carbon. No carbocations for you. Cool. There's one more idea we can evoke here. This will help us with Unit 3. Unit 3 is all about these carboxylic acid derivatives. Okay. Let's take, this is a nice graphic I borrowed off the internet. Here's an illustration of the carbonyl group, C-double bond O with stuff on it. The squiggly lines mean we broke off the rest of the molecule and we're just focused on the C-double bond O. If you put in a carbon and a hydrogen on either side, that makes an aldehyde. If you attach 2 carbons, you get a ketone. If you attach a carbon and then a chlorine, acid chloride, and so on, all these other groups. They all possess carbonyls, right? That's a carbonyl, that's a carbonyl, 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 carbonyl for everybody. But they're all different types of carbonyls, right? Got to keep them separate in our minds. Aldehydes and ketones are one type of carbonyl. These 5 are a different type of carbonyl. We can draw the resonance structures to show stability, but we also talk about reactions. We can say, okay, what happens if we treat these with hydroxide ion? Okay, these are reactions we're going to see in Unit 3. So I don't want to talk about the mechanism now. I just want to talk about how all 5 of these do substitution. which means the chlorine comes off and the hydroxide ion goes on. So put on the hydroxide ion. Hey, acid chlorides react with hydroxide to form a carboxylic acid, and the chloride leaves. Chloride swaps out for hydroxide ion. That's substitution. And hydrides, same deal. This group, an acetate ion, or the anion of a carboxylic acid comes off and the hydroxide ion goes on, carboxylic acid. Thiol ester, carboxylic acid. Sort of like taking the integral, getting rid of the derivative, or going back to the original function. I know some of you are like, no, Dennis, don't be talking math. This is chem. Okay, we're going to just do substitution. Take off the hydroxide group, put in, take off the sulfur group. There's an anion there. And then do the same thing on the ester. Substitute the OR group with hydroxide ion, and out comes second. The leaving group is this O with an R group. It's negative. And finally, hydroxide ion reacts with amides to make carboxylic acid. Yes, it does. And the OH group goes in. The amide ion comes out. You add hydroxide ions to these, and you don't get substitution. You get addition. And I'm going to show you that reaction in just a section. That's just a second. It's an addition reaction. They react very differently. Let's see, what else I have to do here? One way to understand how come aldehydes and ketones do addition, not substitution, and all the derivatives do substitution. It's an old video we keep harping on, the order of basicity video. If you look at the leaving groups, we got chloride, resonance stabilized oxygen, non-resonance stabilized oxygen, and nitrogen. Hey, remember our order of basicity? Go to the top left of the top right of the periodic table. Grab CNOF, insert the anion of the triple bond, and you have the ordering of strongest to weakest base. Fluorine's the most electronegative, making it the most stable anion, easy to form, doesn't want to react. Carbon's like the least stable, can't handle that negative charge, it's not electronegative. It wants to react, making it the strongest base. So acid chlorides react very quickly to produce a very stable anion. This is a resonance stabilized anion. So anhydrides work pretty quickly too. Sulfur is lower on the periodic table. You might recall from Gen Chem, it's less basic than hydroxide ion. So this is actually downhill in energy. We have a strong base going to a weak base. Whoops. Sulfur, weak base. This one is uphill in energy a little bit, right? Hydroxide ion is strong base, but you put some carbons, which are on a benzene ring, they're weak activating groups. The carbon on a base makes it an activating group too. This makes it a stronger base. And of course, hey, order of basicity, negative nitrogen is more basic than oxygen. So how come this reaction goes? We have to drive it by heating it with concentrated sodium hydroxide ion over long periods of time. It's a very slow reaction because the leaving group is more basic than the reagent. If you try and get substitution, then what are you going to do? You have to take off a methyl group, put on the hydroxide ion, and then you get negatively charged carbon. The methyl group, if you're trying to do substitution, has to come off as a negative carbon. Yikes, that's the strongest, most reactive base. Nature says, no way. Ketone, you can't do substitution because that would cause this bad leaving group to show up, highly reactive, strong base. Same is true with the aldehyde. Hydride ion is a very powerful base too, unstable, reactive. Aldehydes, sorry, nature says you can't do substitution either. go by another route, addition. Order of basicity. Cool. All righty, let's see that last reaction for this video, and it's the first of several. So all these addition reactions can be classified as nucleophilic, right? We're going to have some nucleophile attacking the aldehyde or ketone and adding to it. So these are nucleophilic addition reactions. We're going to see the mechanism in a second. It's not going to be SN1 or SN2. There are some aspects that are similar, but it's a different type of addition reaction. Well, SN1, SN2 substitution. Anyways, that's not addition. What am I talking about? What should I be talking about? So in this video, we're going to do one reaction, one of the nucleophilic addition reactions, but it goes by two mechanisms. It just depends on your reagent. You can either use an acid or you can use a base. Okay, and the mechanism changes a little bit. This is a good reaction to start with because we see a acid-catalyzed route and a base-catalyzed route. And the next set of key concepts is going to go through several reactions, and you're going to find features of either the acid-catalyzed mechanism or you'll see features of the base-catalyzed mechanism. So these two mechanisms are the ones we need to focus on first, get comfortable with them, and then we can use these mechanisms to figure out the mechanisms of the other reactions. There will be a lot of similarities. Cool. All right, first let's predict the products. We're going to start with the aldehyde ketone. It's the same for either one. So they'll draw an aldehyde, draw a ketone, and we're going to treat it with an acid-catalyzed reaction. The first of these reactions of many is called hydration. Right? Keep your body hydrated. What does that mean? Drink lots of water. Yeah. So we're going to add water to the aldehyde or ketone under an acid-catalyzed condition or base-catalyzed condition. So properly speaking, our reagent is going to be the acid catalyst plus water. You can actually specify the acid with the water, or you can simply say hydronium ion, which implies you have a mixture of acid with water. We get addition. Addition reactions take the starting material and keep all the atoms. Keep all the atoms. Keep all the atoms to lose. Oh, wait, that's not there. Sorry. Keep all the atoms. Keep all the atoms. But we lose a double bond because the water molecule with an acid catalyst is going to add here. So the water is H2O, so one H, one O stay together. The other H of water goes to the other oxygen. Same deal. The water splits. OH group goes here, the other H goes there. And what you get are two alcohols on the same carbon, a diol, a geminal diol, if you want the word. That's a common name for that type. And that's the product. Cool. The reaction is reversible. So what you do to get it to go backwards is you remove the water. So on this side of the equilibrium, we're taking water, adding the aldehyde, adding an acid catalyst, and we make the diol. You can remove the water and drive the reaction backwards to get the ketone or aldehyde back. In the lab, do I have any notes on how to do that? Nope, must be later. Cool. Let's look at the mechanism. Okay, let's do the one with the ketone. What's kind of cool is after we draw the ketone reaction, just change one of the methyl groups to hydrogen, and you have the aldehyde mechanism. Oh. Same mechanism for aldehydes and ketones. That's cool. Okay, we're going to start with ketone, and we're doing the acid-catalyzed route. So let's add hydronium ion. and let the most reactive reagent go first. Hey, ketone, yeah, you're more reactive than the carboxylic acid derivatives, but you're fairly stable. You use a nail polish remover. That can sit on the shelf a long time. Hydronium ion, ooh, strong acid. You go first. Acid, do your donating thing. Specifically, lone pair is going to pick up an H+. Hydronium loses the H, one of these three H's and a plus, and you're left with water. Water is a weak nucleophile. You might remember that when we talked about SN1 reactions last semester. Weak nucleophile. It needs the acid catalyst to kind of encourage it to attack. Sure, the oxygen's positively charged. The oxygen here is negative. But this carbon is much more positive. It's a better electrophile, if you want a word. And the lone pair on the water molecule attacks this carbon, adds to it, and it bumps up the pi bond. Pi electrons move up on the oxygen as another lone pair. So like what the Grignard reactions did. The oxygen comes in this mechanistic step with two hydrogens and keeps it. At the end of the reaction, though, we need to get rid of one of these H's and a plus, right? We're trying to make two alcohols. So we need a base, and the only base we have is the weak base water. So use another water molecule to remove that H. And we're done. And you get to decide how you want to draw the diol. These two are exactly the same molecules, right? There's a middle carbon with two OH groups. Yeah, middle carbon with two OH groups. Middle carbon with two methyls. Yeah, middle carbon with two methyls. There's the mechanism. You want to see what the aldehyde? H, 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 and H. And there's the mechanism for the aldehyde. Beautiful. No one, you got them both. I'm double checking my notes, make sure I'm not forgetting anything. We talked about being reversible. Yep, we did. Okay, good. Oh, there is another note here. When I cover it, it's the same limitation that we'll see in base-catalyzed mechanism. Hydration is not useful for synthesis. Let me cover that after we talk about the base-catalyzed route. All right, you get the same products. It's just catalyzed by base. So if we take that aldehyde, take that ketone, and we don't use hydronium ion, instead we use hydroxide ion. You can write OH, maybe with a low AQ, or you might write, I think I normally write NaOH with water. What does that mean? Well, hydration reaction again, adds water with the base catalyzing the reaction. It's addition, so keep all your atoms. Yep, the aldehyde keeps all its atoms. Add a water molecule, there's two H's and an O. One H and an O goes here, the other H goes there. Same pattern with the ketone, keep all your atoms, lose the pi bond, add an OH to where one of the pi bond used to be, where the pi bond used to be on the carbon, add an H onto the oxygen, and we have our diols again. It's also reversible. So you just put another arrow here to show that, hey, you can also go backwards. In the lab, here we go. Physically, what do you do in the lab? Well, you can do an extraction. Do you remember using a separatory funnel? Stopcock here. Trip it here. You put, you do this reaction in water, and the water might be on the bottom layer. And then you have a ether or dichloromethane, some organic solvent on top, and you can neutralize the reaction, get rid of the catalyst, whether it's acid or base, and then you can do extraction. And as equilibrium is going back and forth, the ketone aldehyde can't hydrogen bond like the hydrated forms can. So when the molecule switches back to the aldehyde ketone form, it's less polar, and it will actually move up into the organic layer. And you can drain the bottom layer and keep the top layer, which has your aldehyde or ketone. So that's one way to reverse the reaction. You can also distill. So you set up the equilibrium, start boiling it. And again, these are alcohol groups. They can hydrogen bond, higher boiling point because stronger intermolecular force. The aldehyde ketones are sticking together by dipole-dipole forces, not hydrogen bond. So they'll have a lower boiling point. They'll evaporate first. You can distill them, get them away from the water and the diol forms. You can also add drying agents that will just absorb the water, and that will reverse the equilibrium, right? So if I draw a balanced equilibrium reaction here, water plus aldehyde or ketone makes a diol. As you remove the water by absorbing it with calcium chloride or magnesium sulfate, sometimes nicknamed mag sulfate, the water gets removed on the reactant side. Le Chatelier's principle says if you remove a reactant, the equilibrium shifts to the reactant side, to the left, and you'll form your ketone or aldehyde. Nice. All right, we do need to know the mechanism. Like I said, there's going to be more reactions in our upcoming videos, and some of them are base-catalyzed. So know this first base-catalyzed mechanism so you can do the other ones more easily. Well, let's just add Na plus and OH minus. Okay, hydroxide ion is a good nucleophile. Water was a weak nucleophile, and that might be one way to differentiate these two mechanisms. The water molecule is too weak, so while H-hydronium ion is in equilibrium with H plus and water, and you might say, well, how come water doesn't just bump up the pi bond? Well, it's bad at doing that action. It's not a good nucleophile, doesn't like it. Needs some encouragement. The acid has to go on first to make this carbon more electrophilic and kind of draws the water molecule in, because water is a weak nucleophile. But if you switch the base-catalyzed mechanism, you're starting with a good nucleophile, and hydroxide ion says, oh yeah, I sense that slight positively charged carbon, and boom, it's right there, and immediately bumps up the pi bond. The carbonyl oxygen becomes a negative anion. OH adds to this carbon. And now we're trying to make a diol, so all we need is a hydrogen here. We need to neutralize this with an acid. All we have is sodium hydroxide and water. But thankfully water is not only a weak base, it's also a weak acid. So water donate H plus to the alcohol, sorry, the anion of the alcohol. We protonate it and we get our diol. And we also get hydroxide ion back. Water loses H plus. So we start with hydroxide ion and we get it back. It's a catalyst, it's not being used up. And we also form our diol. I like the base-catalyzed mechanism because it's shorter too. But we need to know both. And I think I left out that feature over here. I forgot to point out that when this water molecule grabbed an H plus, we reformed hydronium ion. So we started with hydronium and we get it back at the end. Again, it's a catalyst. The hydronium ion is not being used up. Okay. Really? Long set of 2 videos. Okay, let's end this video with a quick discussion about why hydration is not a useful reaction for synthesis. So, I hesitate to put this on the screen because it might plant a seed in your head. You might say, wait, I kind of remember Dennis doing this. I think it's okay. No, this is going to be bad. So let's put a big old no here. This is not going to work. But here's the situation. I'll have a student on an exam who says, you know what? There's this crazy molecule Dennis is asking me to make, and there's a pair of halides on the same carbon. And I know halides can be made from alcohols. So why don't I just use SOCl2 or PBr3 if I'm trying to make the bromide? Oh, but there's two of them on the same one? Why don't I do this? Start with the diol, add SOCl2, and I get this one. Big no. And the reason why is the proper term for the diol is a hydrated ketone, right? So this carbon has two carbons. It came from the ketone with either acid or with base and water. Water is still here in order to maintain the structure. Remember, it's reversible. If you remove the water, you take away the diol. So if you get rid of the water, you go back to the double bonded form, the aldehyde or ketone form. Why do we need to worry about that? Well, when we add thionyl chloride to an alcohol or PBr3 to an alcohol, the OH group gets substituted with a chlorine or a bromine. If you add thionyl chloride to water, water has an alcohol group in it. There's an OH group in water. So the thionyl chloride is going to react with that to make HCl. If you add water and PBr3, you're going to make HBr. Right? So all you're doing is substituting. Take away the OH. That's what we're doing here. Take away the OH and put on a bromine. So when you say, oh, wait, but there's two alcohol groups, shouldn't I get two halides? Nope, because there's also water in the reaction, and the water is more reactive than this diol. The thionyl chloride is going to go after this and turn it to HCl, and all this will go away, and it won't react with this. Doesn't work. Thionyl chloride, PBr3 are not the only reagents that react with water. So in general, you cannot use a diol for synthesis. I'm sorry, a geminal diol. A hydrated ketone or aldehyde. Hydration is not a useful reaction for synthesis. So if you have a carbon with two alcohols attached to it, in general, we can't use this in synthesis. So don't try and do it. You won't earn points. That's a big warning here. So why are we even showing it? Because it's a fact of life. Over here, acetone has that structure. But if you look up your nail polish remover, you'll discover it's a solution, an aqueous solution of acetone. So the acetone is actually existing as this in solution. It's in equilibrium. Most of the acetone has the diol form because there's water around. And this makes for a good solvent. It's very polar, it can dissolve the nail polish. And this helps too. So they both go after it. Our bodies use carbohydrates as an energy source. We'll learn in Unit 5 this semester that carbohydrates always have either an aldehyde or a ketone. So carbohydrates in the bloodstream, hey, blood is an aqueous solution. They oftentimes exist as diols, which explains why they're so, well, one reason why they're so water soluble, because of all these hydrogen bonding groups. So fact of life, it's kind of necessary evil. Just don't get caught up in using these for synthesis and you'll be set. All right, that's enough for now. I'll see you in the next video.